Hello and welcome to Talk Julia. My name is David Amos.
My name is Randy Davila.
So Randy, we're continuing our discussion that we've had over the last couple of weeks now of machine learning in Julia. We started with looking at reinforcement learning. We did a whole episode on the Flux.jl package and its ecosystem, and we looked at a really simple example of linear regression. This week, we want to take a look at deep neural networks using Flux. So Randy, why don't you show us what you've got for us?
Okay, so right before we started recording, I realized that this is actually a very special topic for me in relation to Julia. Now, there's a little bit of a story here. So years back, like 2016, 17, somewhere around then, I was working on my PhD in pure mathematics, but then also finding myself programming or like beginning to program for statistical and data sciencey type of things. And I came across this playlist by Grant Sanderson and his YouTube channel, 3 Blue, 1 Brown. It is a playlist on neural networks, and it's probably the best playlist on neural networks that's on YouTube.
It's pretty good, yeah.
The animations are awesome, like all of his videos. The descriptions are awesome, like all of his videos. And it's presented in a way that makes you feel like you can understand the topic. So he has 4 videos in this series. The first one is, but what is a neural network? Where he describes the general idea behind feeding data into a network and then possibly training it. But he doesn't go into it in that video. In the second video, he talks about gradient descent. This is the technique that's used to update the weights and biases of a neural network. In his third video, titled What is Backpropagation Really Doing?, he goes into the intuition behind calculating the partial derivatives of the weights and biases in the network through this algorithm known as backpropagation. And then finally, in his fourth video, he talks about the calculus of backpropagation. I was not a Julia programmer when I stumbled across this playlist. However, I knew about Julia from when I was a grad student. When I started looking at how to maybe program one of these neural networks from scratch on this famous MNIST dataset that he uses in his videos, I originally looked at Python because I had experience programming in Python, but the way that NumPy looked did not feel right to me when dealing with matrix operations and keeping track of the dimensions of the matrices that you're using. So if you're not familiar with neural networks, the way that data is fed in is basically a matrix vector multiplication. This just did not feel right in Python. So I started looking at Julia. And again, my goal was to program a neural network from scratch and have it learn with this backpropagation algorithm. So I looked at the way that you could do matrix operations in Julia and immediately found myself saying, okay, this is what I'm going to use. So this playlist, together with the ease of using Julia for matrix operation and a link that's given in Grant Sanderson's first video, but what is a neural network, to a book online that's free called Neural Networks and Deep Learning. These 3 things allowed me to program my very first neural network from scratch in Julia. I watched the videos for the intuition. I went to this textbook for the exact details of the algorithm. And then Julia made it so easy to program. I literally read through the algorithm, typed it exactly as it is, and was able to have my neural network learn this MNIST data set, or learn to perform well on this MNIST data set.
Yeah.
So on that note, I'm going to pull up a notebook real fast that revisits this MNIST data set. In this notebook, we're going to program the exact same neural network that Grant Sanderson uses in his playlist. We're not going to do it from scratch, though. We're going to use Flux.jl, the package that we started exploring in last week's episode.
Yeah.
In that episode, we programmed a single neuron. So a single neuron is a computational unit, and it acts as a function that takes as input a signal, weights it, and then passes it through an activation function and spits out a value. We did this using Flux, and it was surprisingly simple and easy. And I think both David and I were really excited about the syntax that Flux has, right? And the API. Sure. In this week's episode, we're going to stack these together and form a neural network that we're going to train and predict on this MNIST data set. So the MNIST data set consists of 70,000 handwritten digits. So like 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 70,000 handwritten digits, 60,000 of which which are typically used for training the neural network with this backpropagation and gradient descent, and 10,000 used for testing your model on.
Yeah.
So on my screen right now, I have a whole grid of examples of these handwritten digits. And in the show notes, we'll have a link to a GitHub repository with this Jupyter notebook on it so that you can go and play around with it. Okay, so the packages that we're going to import at first will be ML datasets, Flux, plots, images, and statistics. The train X and train Y data, so the images and their labels, can be loaded from ML datasets. And the way that you do this is say train X comma train Y is equal to MNIST dot train data, and I specify float 32 as the type of the values.
Yeah.
And test X and test Y is equal to MNIST dot test data, and then again float 32. Now, David, can you speak a little bit about the troubles we ran into this morning when just trying to access the MNIST dataset?
Yeah. So there's actually a couple things I want to say on that. So you had no problem getting it on your computer. You're using an Intel Mac, right?
Right.
Is what you've got. We had no problem doing it, say something like on Google Colab running, like a Linux OS there. So I'm on one of the new Apple Mac minis that has the M1 processor in it. I have not been able to figure out how to get ML datasets to work. Really, it boils down to one dependency that can't get compiled. And I think it's called binary loader, if I remember correctly. I don't have it up in front of me. But the problem is, first I get a little warning saying that, the ARM64 architecture for the Apple Silicon isn't supported by binary loader. And then it fails when it tries to compile. And then if I try to import any data set from ML datasets, I get some errors about some missing functions or things like that. So it appears that for the time being, and again, I haven't spent a lot of time researching a solution for it. So maybe there is a solution that somebody knows about. And if you do, please, you can send us a message at TalkJuliaPod on Twitter or something like that to let us know what the solution is. But for now, yeah, I haven't been able to get ML data sets to run on the Apple Silicon. The other thing I wanted... Oh, go ahead.
Okay, no, go ahead, David.
Well, I was going to kind of sort of change topics just a little bit and just mention, so you're specifying this float 32. You've got a 64-bit computer. So normally your floating point would be like a 64-bit floating point number, but you're specifying float 32. And that brings up kind of an interesting point that I don't think we touched on in the last episode when we were talking about Flux. And that is that one of the major things that you can do to get better performance out of Flux is to not use any more precision than you absolutely need to. So for example, if all you're dealing with is 8-bit integers or something like that, like specify that you're actually using 8-bit integers or, whatever you need. So in this case, rather than using the 64-bit floating point numbers, you're specifying to use 32-bit because it's going to give you better performance overall. Well, they take up less memory. Right. I mean, so you get better memory performance.
And it actually made a difference too, because I was not specifying float 32 at the beginning and it was slower. And it's something to keep in mind when you're loading this data.
Yeah. And it's actually one of the benefits. So it's one of the maybe confusing aspects of Julia, but also one of the benefits of using Julia is that you get this kind of fine-grained control over the actual types that are being used.
Right.
So that's very hidden in Python. You have maybe a little bit more control. If you're using something like NumPy, you can, have more fine-grained control over it. But in general, like in Python, if you're using a float, you're using a 64-bit floating point number. Anyway, yeah, just wanted to comment on that.
Yeah, and I'm glad you did because I was about to forget about that. Okay, so back to the code in front of me. We have loaded the train data, train labels, test data, and test labels. What are these things? Well, these images are saved as matrices, and they are 28 by 28 matrices. So 28 pixels by 28 pixels. So these are really low resolution images. Mm-hmm. And each entry of the matrix corresponds to a pixel. And the value in those entries is between 0 and 1. One way of representing this that I have on my screen is that the pixel is completely white if the value is 0. And as the value gets closer to 1, the pixel gets darker. So these are black and white grayscaled images. Okay. Yeah. Now, the way that they're going to appear in my code is it's the opposite.
Yeah.
The writing is in white and everything else is black. There is a way to view the matrices as an image, and that's with the color view function that I access through images. I call color view, open parentheses, capital G, gray, comma, train underscore X, that's what I assigned as my training X, brackets, colon, comma, 1, in brackets, and then transpose. Some of you might be wondering what's going on with train X colon, comma, colon, comma 1. That's the first image in our data set.
Yeah.
And our data set actually is stored as a tensor. A tensor is a multidimensional matrix. In our case, we have a three-dimensional tensor. And the shape or the size of our train X is 28 by 28 by 60,000.
Yeah.
So there's 60,000 images and they're each 28 by 28 matrices. And then the labels are just the digit label for that given image. And there's 60,000 of them.
Right. Yeah.
And then for test X, it's a 28 by 28 by 10,000 tensor. And then test Y is a 10,000 entry array of just integers that represent the digits. One way of feeding this data into a neural network, which again, a neural network is a layered sequence of single neurons that we discussed last week. These are just computational units. And in general, the entire network is a giant computational function.
Yeah.
Right.
Yeah. You're just composing a bunch of functions together.
Right. That's actually where neural networks get their ability to approximate any function. So there's a famous theorem that states that if you have a sequence of neurons layered together in a dense neural network, and at least one of the hidden layers in there has nonlinear activation functions, then you can train this network to approximate any reasonable function. So this is this approximation theorem that's famous in the deep learning community. So what that means is that if we're trying to approximate a function that's going to classify digits, then we can use a neural network to do that, right? Like we can find this function, we can approximate this function that is classifying these digits. How do we feed in each entry of data? So each entry of data is a matrix, and what we're going to do is flatten it, which means that we're going to take each column and stack the columns on top of each other and make a giant column vector. And since each image is a 28 by 28 matrix, the resulting column vector will be a 784 entry column vector.
Yeah.
And Flux has a nice function to do that for us called flatten. So we can just pass our data into this flatten function and that will be taken care of. And then next, we're going to create a neural network that takes as input an image and then has two hidden layers with 60 nodes each, and then outputs a layer with 10 entries in it.
Yeah.
And that vector needs to be compared to the label of the input matrix that we sent in. So we need to take these integer labels and convert them to a 10 entry vector. And this is called one-hot encoding. So if we have an image of a 4 and the label is the integer 4, then we will make a vector where if you're in Python, the index would be 0, 1, 2, 3, 4. Mm-hmm. But in Julia, we're going to just call this one hot batch function on our training values to make these column vectors for us.
So each digit, like the number 4, gets mapped to a vector with all zeros except for a 1 in the position representing 4.
Right.
Yeah. Here is where like the whole 1 index versus 0 index thing can potentially be a little confusing with this, because the first entry in this vector represents 0, but it's at index 1 in Julia.
Right.
Yeah.
What you can imagine is happening in this neural network is that we're taking in a matrix and we're feeding in this 784 entry flattened version of it into the network, and it's spitting out a 10-dimensional vector, right?
Yeah.
The label for that is going to have a 1 in the dimension that's important.
Right. Yeah.
The labels with 0, like the 0 labeled images. The most important dimension will be the 1 dimension.
Right.
For label 1, it would be the 2 dimension. And we can think of training these neural networks as mapping the images to those respective regions of space.
Oh, yeah, that's nice.
So the outputs of the network are placing the images in the region of space that is corresponding to these one-hot encoded vectors. It's a really interesting geometric viewpoint of what neural networks are doing when they're classifying. Right. They're literally separating the data in space and placing them in the correct dimension. So I just think that's a really cool visualization there. But back to coding. All right, so I have the flatten function from Flux applied to train X, which I'm going to call xtrain, and then xtest will be equal to flux.flatten testx. And I do that because I want to view the images later. I want to have two different variables, right? One with the flattened and one with the original data, so I can just view them and compare them to what my network is outputting.
Yeah.
And then for ytrain and ytest, I call flux.onehotbatch train y, comma, 0:9. Okay, so those would be the digits, right? And then I'm going to print out the dimensions of X train and Y train. The dimensions for X train are 784 by 60,000. What this shape is telling me is that each column of this matrix is an instance of a digit, right? One of these handwritten digits. And the features or the pixel values are along the rows.
Yeah.
This is different than Python in every way. There are no machine learning libraries in Python that have the features along the rows. Like TensorFlow, scikit-learn, PyTorch, it's standard to feed in the data with the features along the columns.
Yeah.
So this is the way that it's done in Flux, but also in the other machine learning packages I've seen in Julia. The features are along the rows and the instances are along the columns. So that's an important point to note if you're coming to Julia from Python. So next up, now that we have reshaped our data and it's ready to go, we have our flattened images and we have our one-hot encoded labels, we're going to now build our neural network. And I'm building it with the same architecture as shown by Grant Sanderson in his video series. So we have I should probably mention what chain is. David, you might want to talk about that.
So chain's pretty cool. You can sort of think of it as really it's just doing function composition for us. Maybe as like an example of function composition, if you have a function f and a function g, f composed with g, you apply g first to something, and then the result of that you then pass into the function f. So it's like f of g of x would be an example of composing functions. And you can kind of think of it as like chaining things together in a sense. Like first you do one thing, and then you take that output and you feed it into something else, and then you take that output and you feed it into something else, and you can do this over and over again. And that's what chain is doing. And one of the things that is kind of cool about chain, and it goes back to this thing we talked about last week, where these dense layers that you've got here are functions. This Flux.chain function chains all these things together, but it is a little bit different in the terms of the order that things happen when you traditionally think of function composition. So it's applying whatever comes first in the chain function gets applied first, and then the output gets put into the second thing, and then that output gets in the third thing, and so on. Whereas normally like f composed with g would get applied first, and then f kind of like from right to left, whereas this is going from left to right. But you can put any function into it. Like it doesn't have to be like one of these Flux, layers that they've got. Like there's the dense layer and they have recurring layers and there's all sorts of, but it doesn't have to be one of those layers. It can be any function. And as long as all the dimensions and stuff match and you can pass one thing into the other, you can put that in there. And so that opens up some interesting things. You can do like processing of things in between steps of like the neural networks. You can, I don't know, it kind of opens up some interesting possibilities there. But yeah, that's what's going on with chain. It's really just composing these for you.
And actually, I probably should have shared this first. The reason why it's going from left to right has to do with what's on my screen and how neural networks work.
Yeah.
On my screen right now, I have one of the slides from a recent lecture that I gave on deep learning, and it shows that this is a simplified version of what we're doing, by the way. We have 3 input neurons. We have a hidden layer, one hidden layer with 2 neurons, and another hidden layer with 2 neurons, and then an output layer. So the way that this layering structure works is we feed in our column vector into the leftmost neurons, and then that value, that vector, is multiplied by a weight matrix, which correspond to all the weights on the connections between the input layer and the first hidden layer, plus another vector. So it's like W times your input plus B, and that gives you your pre-activation of your first hidden layer. Now that you can think of that as dense, like in this case, it'd be flux.dense 3,2.
Right, in this example, yeah.
However, in order for our neural network to be useful, we need to apply a nonlinear activation function to those values. Right. And we chose the sigmoid function because that's what was used in the textbook that I brought up earlier and was mentioned in Grant Sanderson's videos. The sigmoid function is a function that squishes the values between 0 and 1. So we have this linear combination of the input and the weights and the bias as your pre-activation, and then we apply the sigmoid function to that value. So looking back to my code, I say that model is equal to flux.chain, open parentheses, and then the first layer is a dense layer. We're for the left entry is m times n, which is 784 in this case. And then the right entry is 60, which is the output. We want 60 hidden neurons and 60 neurons to be the output. And we're applying the sigmoid function using flux.sigma.
Yeah.
So it matches up precisely with how I would lecture about it.
Yeah.
And then that value, right? So after you pass through that layer, think of that as like another input layer as before. So then since the previous layer outputted 60 neurons, the next layer is going to input 60 neurons.
Yeah.
And then it's going to output 60 because I want another hidden layer of 60 neurons. And then I apply the sigmoid function again.
Yeah.
Comma, dense. Since the previous one outputted 60 neurons, that means this one's going to input 60 neurons. And now I want this to be my final layer. So I will have 10 output neurons and the sigmoid function will be applied to those. So hopefully it matches up with the visualization on my screen. And I think it does.
And real quick, just to mention that the choice of 60 neurons in like your hidden layers is somewhat arbitrary. Like you could change that. I mean, the important thing is the input and output has to be the right size.
Right.
Like the first input and the final output. And then what goes on in the middle, you can play around with that. So for people listening or watching, there's not necessarily like we didn't magically know that like you have to use 60. It's sort of a choice you get to make.
Right.
And you can kind of see how things perform and maybe change that.
The only reason why I chose 60 and 60 was because I wanted to mirror in today's episode, I wanted to mirror what was shown in that playlist by 3 Blue 1 Brown and Grant Sanderson, because that's the structure that he chose.
Oh, really? I thought my memory it's been a long time since I've seen it.
It's either 66. Oh, no.
Doesn't really matter.
Yeah, it's very similar in any case.
Yeah, it's the exact same thing. We might have a different number of neurons.
But again, our listeners can go and fix it because this code will be available and run it exactly as it should be.
Yeah.
So then next up, we have a loss, and I'm choosing a very simple loss function, the mean squared error loss function, which we discussed in last week's episode. Mm-hmm. So loss x comma y is equal to flux.losses.mse, open parentheses, and then model is the network that we defined, which is a function. So model, open parentheses x, comma, y, close parentheses. So that's our loss function. And then we have an accuracy function. So we want to know how accurate our model is, right? Like what percentage of the data is it getting the correct answer on?
Yeah.
So accuracy x, comma, y is equal to statistics.mean, open parentheses, flux.oneCold. So that's grabbing the label out of that vector that it was. So oneCold model x dot equals flux.oneCold y. Mm-hmm. So it's taking the average out of all of those times it equaled, right? So we should probably mention, though, that we're using statistics.mean here instead of just saying mean, because we would like to emphasize that the mean function comes from the statistics package.
Yeah.
You don't have to use statistics.mean. It's just for our purposes, we've kind of fallen into the idea of using this just so for people that are coming to Julia and are new to Julia, they know where the functions come from. So that's the only reason why we're using it.
Because we imported it with using statistics. So as long as mean is exported by that module, which it is, you don't have to do statistics.mean. Yeah. And we kind of experienced this when we were prepping for this. There were lots of times we're going through and like, where does this function come from? Is it in statistics? Is it in like all these other things? Well, the mean one, I guess it was pretty easy to know that comes from the statistics module, but there's other examples that, I was looking at it, it's like, where is this coming from? I think we've talked about it a little bit in one of our earlier episodes, but just to kind of reiterate this, it's always funny saying this, when you're using, when you import something with using, it's fantastic for like working in the REPL and having quick access to these functions, and you don't have to type as many characters, and that's great. And you should do that if you're comfortable with all that and everything. But just keep in mind that then if you go share that code with someone who's maybe new to Julia or still beginning, or maybe just new to some of the packages that you're using, it can be something that causes confusion. And of course, there's tools. You can always use the help function or the help mode in the REPL to look up stuff and everything. So there's ways to investigate all of that, but it can be confusing when you're reading code like that. So
yeah, it's something that I think that will just keep on. I'm going to keep on doing it when we're presenting. So now that we've defined our model, our loss function, and our accuracy function, we next need to define an optimizer. Now I'm choosing the Flux.descent optimizer with a learning rate of 0.23. Now, this is not the optimal optimizer in many cases. In many instances, you would rather use Atom or something else. But because I'm trying to mirror the playlist from 3 Blue, 1 Brown, I'm using just straight gradient descent, or as you'll see, stochastic gradient descent. And then I format my data. So data is equal to open bracket, open parenthesis, x train, comma, y train, close parenthesis, close bracket. And then I collect my parameters from the model. So parameters is equal to flux.params, throw in model. I print out my loss, I print out my accuracy, and then I call the flux.train exclamation mark function and pass in my loss, parameters, data, and my optimizer. And then I print out my new loss and accuracy. I should note, again, this is full gradient descent. This is not stochastic gradient descent, meaning the gradient is computed with respect to every single entry of data. So the 60,000 entries of the training data. And then gradient descent is applied to update the weights and biases. In practice, this can be very slow. For example, if you ran this same code that I have here with the for loop and looped this train bang function like 100 times, it might run for like 10 minutes. But we can get around that by just calculating the gradient with respect to a random entry of data at a time and then applying gradient descent. So this would be stochastic gradient descent. What I'm going to do is I'm going to loop over 100,000 epochs. So for 4 epoch in 1:100,000, I randomly select a integer between 1 and 60,000. And then I say data is equal to open brackets, x train, open brackets, colon, comma, I, close brackets, y train, open brackets, colon, comma, I, close everything out. So data is now just a single instance of the training data.
You're picking a random image, basically.
A random flattened image in this case.
So yeah, random flattened image and the corresponding label for that. Yeah.
And then I pass that data into the flux.train exclamation mark function. So that will be computed 100,000 times. And then every 10,000 times, I'm going to print out the epoch and then the loss and the accuracy using this @show macro, which I just found out about recently.
Yeah.
So @show will print out the function with the variables that you pass in it equals to the value of the function. It's similar to passing into an F string in Python in curly braces like x equals, and then it will print out x equals whatever its value was. It's a really cool function. So now I'm going to run this. All right, so yeah, it took 40 seconds to finish, and we can see that the loss is decreasing and the accuracy is increasing. So by the time we finish, we are 93% accurate. That's pretty good. Our mean squared error is 0.01. That's pretty good as well. So then if we make a prediction on a random digit, we see that, oh, that's a 1. We predicted a 1. That's a 2. We predicted a 2. And I'm satisfied. This learned.
Yeah, 93% accuracy is pretty good. Yeah.
And that's on the test data. So these are images that the network has not seen. That's important.
Right.
There's one last thing that I wanted to mention, and that's TensorBoardLogger.jl. And actually, I think, David, you might have a few things to say about what TensorBoard is.
Yeah. TensorBoard is a really cool tool that comes from the TensorFlow ecosystem. In fact, I think it's actually built and maintained by the same people that do TensorFlow, right? TensorBoard is a way for you to visualize machine learning results and things like that. So you can do stuff like track and visualize metrics like loss and accuracy. You can visualize the graph of the model, including all the operations, the layers, everything like that. You can view histograms of weights and biases as they change over time, and all sorts of other stuff, displaying images, text, even audio data, projecting embeddings to lower dimensional space. But here's the deal. So we're talking about TensorFlow right now, but we've been using Flux this whole time. TensorBoard is, the way that it works is, while you're training or doing really anything, you can log stuff to a file in a specific format. And then this TensorBoard runs as like a little web app, and it will read from that log file and then display the results in the web app. So when you run TensorBoard, you tell it like, here's where my logs are. And then it spins up a little server and says, okay, you can go to localhost, whatever port, and view the TensorBoard. You don't have to use TensorFlow in order to use TensorBoard. You can write to these log files in the correct format, and then TensorBoard will be able to visualize those for you. So yeah, so if you're using Flux and have used TensorBoard in the past, you can do that with this TensorBoardLogger.jl.
So let's go ahead and show everyone how to do it. So I'm using TensorBoard Logger and logging. So logging is a built-in package. You won't have to add it, but you will have to add TensorBoardLogger.jl.
Yeah.
And David, what's going on right here?
This line of code, we're setting the logger. So we've got a variable called logger equals TB logger. That is the logger coming from the TensorBoard logger package. And we're telling it where to write the log. So we give it a path. In this case, you said content/log. So it's in a content directory with a log directory underneath that. And inside of that is where it's actually going to write out the logs for everything. So we've got TB logger. And then the first argument is, a string with the path to where you want the logs to be saved. And then the second argument is this TB underscore overwrite, which is telling telling it to just overwrite that log each time you rerun. You don't have to do it this way. This is like reusing the same logging file and overwriting it each time. If you wanted to, you could have it create a new one, and then you'd be able to save the logs from all of your different runs and maybe compare and contrast different things if you wanted to. But in this case, we're just going to overwrite each time. And then there's this with logger function that comes from the logging module. This is not from TensorBoard Logger. What this is going to do right now is log some image samples
using TB image, which is a TensorBoard logging.
Right. So logs a few images for us. So this is an example. So you do with logger, and then that's a function you pass into that the logger that you want to use. In this case, it's our logger variable we created as the TB logger. And then you can do stuff inside of that and it will log whatever is going on. So we create an images variable here and use this TB image to get some of the images in the right format that we need for the log file. And then we use the @info macro to actually create the log entry. And we give it a name MNIST/samples. So this is we'll see it when we actually open up TensorBoard in a little bit, but it's creating you can kind of think of this as sort of a space in your logs where you'll be able to go and see these, just some organization there. And then we have pics equals images. So we're telling it the pictures we want are those images, and that'll log everything for us there.
And then the following functions are literally copied from TensorBoardLogger.jl. So the first function, fill param dictionary, making a dictionary of the information of your model.
Mm-hmm. Yeah.
The next function is the important one, though. This is the one that is actually doing the logging. It's called TB callback. And again, I pretty much copied this from TensorBoardLogger.jl. I had to change the names of the entries in our loss and accuracy functions because I have different variable names for those entries. But again, we have this with logger do @info model, and then we look at the params dictionary that we have. So that's the parameters of our network.
Yep.
@info string train, that will be you have your loss on your train and your accuracy on your train. And then info test, loss on your test, accuracy on your test.
You don't have to use these names or anything. You can customize all that however you want, but this is kind of a pretty, I think, standard kind of setup.
So then in the next cell, I repeat the code that I have above, except for this time, I define my optimizer to be the atom optimizer. And I'm not using stochastic gradient descent. I'm just using that optimizer in Flux.train 100 times. So over 100 epochs, I am training this new neural network.
Real quick, before we show them anything, we need to mention where we're actually using that callback.
Oh, yeah, you're right.
So when you call your Flux.train function, you've got, you have to pass it all the normal stuff, the loss, the parameters, the data, the optimizer, all that. But then there's this additional parameter called CB, which stands for callback. And you've set that equal to Flux.throttle. So what that function does is it'll call a callback function, but make sure that it's not called more often than you need it to be. So in this case, it's calling the TB callback function we defined earlier, and it's throttling it to only be called once every 5 seconds.
So it's currently logging right now.
Yeah.
So we can view what's happening. So David, what's the syntax here? So I opened up my terminal now.
So you want to type TensorBoard. So when you install the TensorBoard logger and everything, you get this TensorBoard command that's really with any TensorBoard installation, but it's a TensorBoard command and then --logder. So this is the flag that's going to tell it where to look for the logs. And then you want to give it wherever you put the log. I think it was content/log. And when you run that, you'll see it'll say starting up TensorBoard and everything. And then it will give you the URL to where this is being hosted on localhost so that you can open it up in a web browser and actually look at the results.
All right, so this is what it opened up, and that's its performance. As you can see, it's test loss was decreasing. Train loss was decreasing. I only did it a few times. I didn't specify.
Yeah, you did what, 100 epochs here? So I guess real quick, just to kind of explain for people that are listening and not watching this. So TensorBoard gives you this sort of dashboard view, and it's got some graphs and stuff. So we were logging the current loss that we had during training and the current accuracy that we had during training. And then it was also doing that on the testing data. And in this case, because we only did 100 epochs, you see the loss did go down, but the accuracy stayed roughly the same. Maybe it went down a little tiny bit, but it's only at around 10% accurate.
If you think back to the TB callback function that we made, we called info 3 times, and 2 of the instances were train and test, which we see train and test here.
Yeah, it gives you like these little sections in your in TensorBoard, and you can actually close those. I think if you on the right hand side, there's like this little arrow, so you can close those and everything. And then we also logged at the very beginning, before we did any of this, we logged some images. And if you go up, there's like a main navigation bar over to the left where it says images. And there you can actually see like some sample images. So this is just showing that you can log images if you want to. This actually isn't like pertinent to the training or anything. But if you had, say, for example, you were doing some training on something and there was like an image representation of that and you wanted to actually log that, you could. And you can log not just images, but all sorts of stuff, including like audio and things like that. And then here under the distributions, so the third thing we put in our callback was the model. We called it model, and we were passing the parameters to it. And so here
as a dictionary.
Yeah, as a dictionary. And so what it allows you to do is now we can see for each of the different layers. So I think, you had 4 layers in this model. You can see how those parameters for each layer are changing over time.
Right. Yeah, that's exactly
what
we're reviewing.
Yeah.
Yeah, this is just awesome.
Yeah, it's a really handy tool to be able to just visualize these results. And then what's also really cool about it is you can take that log file and then like send it to somebody, and they could pull up and see your results as well in TensorBoard. So you can share those logs with people if you want to, and they'll be able to look at the results.
It does slow down the training though.
Oh yeah, of course. Yeah. Yeah, because at each step you're having to do all these calculations, and there might be some way to boost that performance by maybe doing some of the stuff asynchronously, but I don't know how to do that in Julia yet. The way we did it, it was all synchronous. So at each step, it was pausing training and it was calculating the loss, the accuracy, and logging all that stuff. So when you do that, you will notice that, okay, training time increased in some cases by a lot, depending on how expensive whatever you have to do is. So definitely something to keep in mind. But if you do machine learning, and especially if you work, I think, on a team, like, and you want to be able to like keep these logs and then share them with other people, TensorBoard is a really neat tool to do that.
Right. I was just thinking it'd be nice to pair with reinforcementlearning.jl.
Yeah, for sure. So Randy, thanks for hanging out again this week and talking Julia with me.
Yeah, thanks. It's been fun.
All right. Well, I'll see you next week.
All right. See y'all then.
Bye.